Okay, so today we're going to look at section 5.1, eigenvalues and eigenvectors. These are some funny sounding words. This is how we pronounce it, eigen. So we're going to have two things that are very related. They really go together nicely, but in order to get there, in order to start, what we have to do is we have to go back and start thinking about our matrix A as a linear transformation, as T sub A. Remember that each matrix we can think about as a map from Rn to Rm, as a linear transformation where I input a vector, I multiply by the matrix A, and that gets me an output. All right, so we input vector x, and we output vector ax. All right, so we get this map from Rn to Rm, where n and m correspond to possibly the rows and columns of this matrix in the right order. All right, so we're going to think about these maps, and a lot of them that we're going to think about for right now, we're going to think about, remember that if I have a 2 by 2 matrix, then this is a map TA from R2 to R2. And if I have a 3 by 3 matrix, well, that's a map from R3 to R3. Where I think about this is my input, I take x as my input, multiply by the matrix A, and that gets me my output. That in this case will still be an R2. In this case, the input and the outputs are both an R3. All right, now, so just to get us on the right path, remember that so suppose that I had some matrix A. Maybe I have the matrix 2, 1, 0, 3. All right, so if x is equal to 1, 2, then ax is equal to 2, 1, 0, 3 times 1, 2, which is 2 plus 2, which is 4, and 0 plus 6, which is 6. So I'm thinking about this again as my input is the vector 1, 2. Let's make space for everything though. So 1, 2. Here's my input vector, x. And then the output vector is this vector, 4, 6. So that was 1, 2. So 3, 4, 5, 6. So the output vector is way up here. All right, 4, 6. All right, so we can think about if I vary this input vector, well, and I've changed it to anything I want it to be, well, that's going to vary the output vector as well. And so if I move around the first vector that we started with x, well, the output's going to change as well, and we can think about all sorts of different pictures happening. When we talk about eigenvalues and eigenvectors, we're worried about one very specific thing. We want to know when is the output almost the same as the input. And by almost, I mean in the same direction. When is the output, AX, in the same direction, or possibly negative direction, but it follows the same line? As the input. All right, so we're worried about a situation where we might have an input vector x and the output vector is in the same line. So this is ax, or maybe possibly backwards, but still along the same line, in the same direction or opposite. So that's our question. And so if I have a vector that works like that, that vector will be called an eigenvector. And we'll write this down and be more precise about it. But the length, the scaling length that corresponds to this situation is going to be the eigenvalue. So the eigenvalue is how much you scale by when this happens, and an eigenvector is the vector which we input in order to make that happen. All right, so let's take a minute. We're going to look at a little interactive figure on the computer that's going to illustrate what I'm talking about in a little bit more detail, and then we'll come back and work out some actual problems and figure out how we might find some eigenvectors and work with eigenvalues as well. Okay, so in this picture, in this graphic, what I've done is I've used the Mathematica program, which you're not going to actually have to use in this class. You do actually have access to this program as an Oakton student. It's something that you can download and use. There's a link on the My Oakton homepage. But you don't have to do this. You don't have to understand the syntax that I've used here. But what I've done is I've told Mathematica to graph two things. The red arrow that we see is just an input vector x. The blue arrow is the output vector ax, where A is actually the matrix that we see up here. This doesn't look as pretty as we might like, but this is just a 2 by 2 matrix. 2, 1 is the first row, 0, 3 is the second row. Right, so this is my input matrix M. So the input vector is the red one. So this is our vector x. The blue is A times x. And remember our idea, right? So the idea is to think about changing the input and see what happens to the output. So if I change my input, if I just make this input bigger, if I just scale the input, well, it scales the output, right? And I can spin it around too, right? So I can spin my input around and see what happens. Well, the output also changes. Now, what are we looking for? We're looking for points or vectors where the output is just in the same direction as the input, or possibly opposite. So we want to say, are there any vectors that I can input? Are there any red vectors where the output, blue, is just a scaled version of the input? Well, now we seem to be getting closer and closer and closer, and at this point, it certainly seems like the output vector is just a scaled version of the input. And if I push it out, well, that's still true, right? So any vector along this line here seems to be a vector where the output is just a scaled vector, a scaled version of the input. Right? And so that seems to happen once. Now, what is the scaling factor? Well, that's not particularly clear, but it seems like a reasonable guess to say at this point, how long is the blue vector? Well, the blue vector is about 3 times as long as the red vector. And that's actually what's happening here. Our scaling factor, remember, is going to be our eigenvalue. And this red input vector will be the eigenvector. And so this actually is a matrix which has an eigenvalue that corresponds to 3. And it certainly appears like the input vector is somewhere around 1, 1. But also any scaled version of that as well. So it looks like this is along the line y equals x. We'd have to do some more work to make sure that that's the case, but that's a reasonable guess. Does that happen anywhere else? So if we spin around, now the vectors are not in the same direction, but now they're getting closer, and now it certainly appears like the vector right along the x-axis is also an eigenvector because the output is a scaled version of the input. And so now what else is happening? So if I make that input vector 5, the output vector appears to be 10. So this seems to correspond to an eigenvalue of 2. I've scaled my input by 2. So we had 2 different places where this seemed to work. Here's one along the line y equals x. Here's another along the x-axis. Notice that happens actually on the opposite direction as well. If I spin all the way around to the other side, this is the same thing. This is really the same this is the same direction as our x-axis, so we're moving along the x-axis, and also if we move along this line y equals x, we have another eigenvector because the output is a multiple of the input. And so this is what we're looking at when we're looking at eigenvalues and eigenvectors. We're looking to see if we have any directions that I can input where the output is just the same direction or possibly negative along the same line as our input. So let's look at another one and see what we can decide. I'm going to change this matrix up here. I'm going to change it to the matrix 1 minus 3 minus 4, 5. So 1 minus 3, that's our top line, minus 4, 5. That's our bottom line. So we're changing that matrix. And now we've changed this as well. Remember, our red is our input vector and blue is the output. And we want to ask the same question. Do there appear to be any directions which I can input for which the output is a multiple of the input? And already, actually where it started, it certainly looked like there was one, right? So now multiple, remember, can be a multiple in the opposite direction as well. Right, so right here where we started appeared to be something that was good because the output is a multiple of the input. What does that multiple look like? It looks like it's just the opposite direction, and the length of the blue is the same as the length of the red. So that means that what have we scaled this by? We scaled it by -1. So -1 seems to be an eigenvalue. What is this eigenvector? Well, that's not real clear, but again, we'll look at this, but a reasonable guess is 3 in the x and 2 in the y. So 3, 2 seems to be an eigenvector corresponding to an eigenvalue of -1 because we scaled it by -1. Did we have any other ones? Well, let's keep spinning it around and see what happens. No, 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 but now we seem to be coming back together. Here's another one which seems to actually work. This one's not clear at all what the vector is or what the scaling factor is, but the scaling factor seems to be big and positive, right? Because the output is in the exact same direction, not the opposite. Opposite direction would be a negative eigenvalue. But so now we seem to have a reasonably large, this seems to be scaled by, I don't know what, certainly more than 5, because this is more than 5 times as long as our input. And so we had one eigenvector here. We spun things around, we found another one, we keep spinning, and now we're back to the first one, right? This is really the same thing because this is the same line that we started with, and then we come around and now we're back to that second one because that's actually the same line as this one that we found down here. And so there's always going to be two, seems like there's two, but they correspond to the same thing. Right? So we seem to have 2 eigenvalues, and each of those eigenvalues has a single eigenvector that moves in that direction. All right, so we'll go back to the whiteboard. We're going to actually look at this matrix, 1 minus 3 minus 4, 5, and show that it has two eigenvalues and find the corresponding eigenvectors. So, in our previous discussion, we looked at this matrix, and we decided that based on the picture, it's a reasonable guess that we have an eigenvalue of -1. We saw that there was an input vector whose output vector was exactly opposite of it. Right? So that would correspond to an eigenvalue of -1. So what we want to do here is actually show that this is the case. We're going to be very explicit and show that this matrix has an eigenvalue of -1 and find the eigenvector. We're going to show that this is true. -1 is an eigenvalue. And we're going to find the eigenvector. We also could make a reasonable guess about the eigenvector, about where it is based on our pictures that we looked at, but we're going to be very precise and find out exactly what it is. So remember what we're trying to do here is we're trying to say, when is the output equal to a scaled version of the input? So we've got, that's what it means to be an eigenvector, when the output is just a scale of the input. So, but the output is AX, and the input is X, and I need to scale this by something, I don't know what, but the symbol that we're going to use all the time is lambda. So this lambda is our eigenvector, eigenvalue, the number. The scaling factor is the eigenvalue, and X is the eigenvector. So if we can figure out for what X we can find a lambda that makes this work, well, that's the eigenvector and the eigenvalue. So the trouble with this is we really have 2 unknowns here, right? All we're starting with is in general, we're just starting with a matrix A, and you'll be asked to find eigenvalues and eigenvectors. We have a guess for an eigenvalue, so we have something we can put in for lambda, and then solve for x. But in more general cases, we may not even have a guess, and we might not have any idea what the eigenvalues are. So there's really two unknowns, and in that case it becomes a little bit trickier, and we'll have to do some more work. But for right now, we do have a guess for the eigenvalue. So we can actually put ax equals minus 1 times x, and say, now I just have a single unknown, the vector x. And when does that work? So we're going to do a few tricks here. Keep my matrix and my eigenvalue. We're going to do a few tricks and see what we can do to solve this. I'm going to bring this over to the left, and that becomes ax plus x is the 0 vector. So I just put everything on the left. I'm going to notice that x as a vector is just the identity matrix times x. Right, so the identity matrix, remember, is the matrix which has 1s on the diagonal. So I times x is just x, which means that now I can actually factor an xl on the right. And now I can say, what does a plus ix look like? I has 1s on the diagonal, so when I add that to a, what I get is 2, because I have a 1 on the diagonal, and I get a 6, but the other pieces don't change. All right, so this is just 1s on the diagonal, so that changes that to a 2 and that to a 6. But this is just a good old matrix equation that we know how to solve. We solve that by row reducing. Right, so we row reduce 2 minus 3 minus 4, 6, 0, 0, and see what we get. That's what we're looking for. We're solving the ax equals 0. This isn't a anymore, but a matrix times x equals 0. So we row reduce, we see what we get. Well, this one's pretty easy because if I take 2 and add, then this becomes 0, 0. Right, and so then I'm going to end up getting 2 minus 3, 0, 0, 0, 0. That's our first step. And then we can go one more step because we really do want that first pivot position to be a 1. So I get 1 minus 3 has 0, 0, 0, 0. Which means that the matrix equation that we started with was consistent because this last line is okay. Right? So it's consistent. It's consistent, which means that ax equals negative x has a solution, because that's where we began. Which means that negative 1 is in fact an eigenvalue, because when I plug negative 1 in for our lambda, we get a system of equations that actually has a solution. We get a consistent system of equations. So how do I know if something is an eigenvalue? Well, if I plug negative 1 in for lambda in ax equals lambda x, that's what we're always going to be looking at. If I plug our eigenvalue in for lambda, and I end up getting a consistent system, then in fact this is an eigenvalue. Because that means that there is a solution. Now we can do better here. We can actually figure out what that solution is. So that solution based on our row reduction is x1 minus 3 has x2 is 0, x2 is free. Which is to say that x1 is 3 has x2, x2 is free. So the vector x is x1, x2 is x2 times 3 has 1. Which means an eigenvector is this. So in fact, any multiple of this vector is still an eigenvector. But this is the fundamental one that we get by working out our solution. So this is an eigenvector for the eigenvalue negative 1. All right, let's look at some more. Before we look at some more, let me talk about it just in more abstract terms just for a minute. Remember what we just did there? We started with ax equals lambda x. We actually plugged -1 in for lambda, but in general we can think about this as just what we actually did. If I bring this over to the left, I get ax minus lambda x equals 0. And then I factor an x out on the right. This becomes a minus lambda times the identity equals 0. Because we're thinking about this now as, if I factor my x out, I need a lambda times the identity instead of just the identity. In the case that we just looked at, we put in lambda to be -1, which is why that became a plus. But this is really what we're going to be thinking about most of the time when we think about eigenvalues and eigenvectors. A minus lambda I. And then row reduce that to see if we get a consistent system. So, let's look at this one. Let's show that lambda equal 3 and 2 are eigenvalues. And this is in fact always the case. If we have a triangular matrix, a matrix which has zeros below the diagonal, even if it's a 3 by 3 or 10 by 10, the eigenvalues will in fact be the entries that follow the diagonal. But we can show that that's true here very explicitly. Let's look at, so we'll show that these are the eigenvalues and find the corresponding eigenvectors. All right, so for lambda equal 3, what we're looking at, remember, is a minus lambda I times x equals 0. But if lambda is 3, then lambda I is 3's on the diagonal. So when I take 3's off the diagonal, this becomes a 0, this becomes a -1. I subtracted 3 because a minus 3i. But the other stuff doesn't change. And so this corresponds to 0, 0, -1, -1, 0, 0. Which row reduces to, if I row reduce, I'm just going to subtract those two rows, and then I can scale this to make a positive one, and I get 0, 1, 0, 0, 0, 0. You can put that into your calculator if you don't like what I just said, but you'll find that it does row reduce to this matrix, which is consistent. So that means that lambda equals 3 is an eigenvalue. What is the corresponding eigenvector? Let's keep our A back up over here. The corresponding eigenvector I get by then saying this is x1, this is x2. This says that x1 is free and x2 is 0. All right, because if I read that top row, this reads x2 is 0, but x1 is non-pivot, so x1 is free. So this means that x, which is x1, x2, is x1, 0, which is x1 times 1, 0. So the eigenvector is 1, 0, corresponding to lambda equals 3. So for lambda equal 3, we got the eigenvector 1, 0. Let's look at the other proposed eigenvalue, which was 2. If lambda equals 2, then we're looking at a minus lambda I times x equals 0. That's always what we're looking at for eigenvalues and eigenvectors. So this is a minus 2i x, which if I subtract 2, 2i is 2's on the diagonal. Subtracting 2 becomes 1 and 0 on the diagonal. The other ones don't change. Which becomes this system, which again is consistent because the bottom row is 0, 0. So in fact 2 is an eigenvalue, and this corresponds to x1 minus x2 is 0, x2 is free. But this becomes x1 is x2, x2 is free, which is x1, x2 is x2, x2, which is x2 times 1, 1. So for lambda equal 2, we get the eigenvector 1, 1. Let's do one last thing with this example, just so that you can see what happens. Let's show that lambda equals negative 2 is not an eigenvalue. All right, so what are we looking at here? We're still looking at a minus lambda I x equals 0, which is a now plus 2i x is 0, which is, now if I add 2's on the diagonal, becomes 5 and 4, 0 minus 1, 0, 0. And we ask, what does this row reduce to? In fact, it doesn't even matter. We already see that there's, well, let's see what happens. So if we row reduce this system, what we get is 1, 0, 0, 1, 0, 0. And this says that the vector x is 0, 0. And so while that does, it is a solution, what we're getting is the trivial solution to that system of equations. This is always going to work. If I were to look at ax equals lambda x, well, x equals 0 always solves that. So when we're talking about eigenvalues and eigenvectors, we're looking for solutions x which are not just 0, because 0 will always solve this equation here. So there are no non-trivial solutions. Which means that lambda equals negative 2 is not an eigenvalue. All right, so while we're here, we will do one last other thing. If I give you just a vector, you should also be able to determine, without much work, whether it's an eigenvector. So is this vector, how about 1, negative 2, an eigenvector for the matrix that we started with here, 3 minus 1, 0, 2. So we're looking at, is ax equal lambda x for any possible lambda, but we can actually figure that out pretty easily. And so by simply calculating a times x, we find that the product is 3 plus 2, which is 5, and 0 plus negative 4, which is negative 4. And the point is that this resulting vector is not a multiple of the input vector x. So this is not a multiple of x, which means that it is not an eigenvalue, not an eigenvector. So what we discovered is that it's really easy to find that if a vector is an eigenvector of a matrix, we simply have to multiply. If we get a multiple of the input vector, we do, then we have an eigenvector. Otherwise, we don't. Figuring out if something is an eigenvalue takes a little bit more work. We actually have to row reduce a matrix and see if we get and has a free variable. Now, so what we'll just do next is move over to looking at some Mathematica. So we're going to actually look at this with an interactive figure, look at this matrix and discover that it really does have the eigenvalues and eigenvectors that we thought that it should, and take it from there. All right, so here's our matrix. I've input the matrix already, 3 minus 1, 0, 2. This was a diagonal matrix. We discovered that it had two eigenvalues, 3 and 2. The eigenvector corresponding to 3 was 1, 0. The eigenvector corresponding to 2 was 1, 1. Let's just see if that matches when we look at our figure. All right, so so 1, 0 we found should correspond to an eigenvalue of 3. Well, 1, 0 is right here along the x-axis. And so 1, 0, our input is red, that's right at 1, 0. Notice that the output is in the same direction at 3, 0. So our output is 3 times as long as the input. And so that certainly seems to match the analysis that we did. Also, along 1, 1 was the other eigenvector. That appears to be right about here. And again, we see that the output is a multiple of the input. How long? The output is about twice as long as the input. So again, that matches. Are there any others? Well, no, there are no others. Right, if I spin this around along the line y equals x, that's 1, 1. That's our first. If I come down, well, now it's moved away, but moving back in, here's the second. And then they're not matching, not matching, not matching, not matching, until we get around to the line y equals x, where they match again. And then they match along the y-axis, or the x-axis yet again. And then they're gone until we get back to y equals x. So as we discovered, we have two eigenvalues, and the eigenvectors match what we expected them to as well. All right, and so let's look at an example now in a 3 by 3 case rather than a 2 by 2 case. It's really the same thing. For a 3 by 3 case, our input vectors are vectors in R3. The output's another vector in R3. We're asking the same thing, right? So is lambda equal 3 an eigenvalue? Well, we're asking, is ax minus lambda x, lambda I times x equal to 0? Is a minus lambda I x equal to 0? That's what we're asking. But now I is the identity in 3 by 3 matrices, which is 1's on the diagonal. So now if I subtract 3 along the diagonal, I get 1 minus 3, 2, and then nothing else changes. Okay, so let's row reduce this one. So again, what are we really looking for? We're really looking for this with zeros, and we're looking for the reduced row echelon form of that matrix. So we can do that by hand without too much trouble, but let's just put it into our calculators, make sure we get the right answer. Okay, and so what we get is 1, 0, 0, going down, 0, 1, 0, minus 1, minus 2, 0, 0, 0, 0. So this is our reduced row echelon form. So we look at this and say, we should be able to answer now, does lambda equal 3 correspond to an eigenvalue? And the answer is yes, it's consistent. But not only is it consistent, I have a free variable. So I have a non-trivial solution. Right, so consistent, non-trivial. Solution. So that tells me that lambda equals 3 is in fact an eigenvalue. All right, so what is the corresponding eigenvector? The corresponding eigenvector I get by writing the solution to that system in parametric form, which becomes x1 minus x3 is 0, x2 minus 2x3 is 0, and x3 is free. which says that x1 is x3, x2 is 2x3, x3 is free, which becomes x is x1, x2, x3 is x3 times 1, 2, 1. And so this is the eigenvector. This is in fact what we're going to call, it is a basis for the eigenspace corresponding to lambda equal 3. We'll see that sometimes remember when we write a solution to a system in parametric form, we may end up with 2 free variables or 3 free variables, in which case we're going to have 2 or 3 different vectors. And each of them are going to correspond to different eigenvectors, both corresponding to lambda equal 3 if they all came from that. We'll look at that more in detail in the future. But for now, this is the fundamental vector that we get back, the eigenvector. It's not the only eigenvector, remember, because we can scale it, and it still is an eigenvector. But it is a basis for the eigenspace corresponding to lambda equal 3. Okay, so lastly, for this section, what about lambda equals 0? So we said that x equals 0 is we're not ever going to call an eigenvector because every matrix will have ax equals lambda x, and x equals 0 will solve that. But not every matrix will have this as an eigenvalue. So when is ax equal to 0 times x? When does that actually have a solution? Well, that's the same thing as saying, when does ax equals 0 have a solution? A non-trivial solution. That is not just 0, right? Because I can always plug 0 in, but 0 we're not calling an eigenvector. So when is that true? Well, that's true if if A0 has a free variable, but that's only true if A doesn't reduce to the identity. But that's only true if A is not invertible. So if A is not invertible, then 0 will be an eigenvalue for A, and the other way around. If we end up getting 0 as an eigenvalue, then I can say for sure that A is not invertible. All right, and that's what we need from 5.1. Next, we'll be looking at 5.2, which is an application of these. And then after that, we'll move into actually finding eigenvalues from a matrix just to start with, which is a bit trickier.